This is Mr. Beck Does Your Homework. AP Physics, homework number 12.1, questions 5, 6, and 7, a three-part question. It says, light of wavelength 649 nanometers in a vacuum passes through a piece of silica with an index of refraction of 1.484. Find the speed of light in silica. So the first thing we need to know is that our index of refraction equation tells us that n, the index of refraction, is the speed of light in a vacuum divided by the speed of light in the substance. So if I'm looking for the speed of light in silica, what I'm looking for is v. So I can rearrange this equation and say that v equals c divided by n. C, of course, is 3 times 10 to the 8th meters per second. And n, in this case, is going to be 1.484 for me. 1.484. And that will give me the speed of light in silica. The second question says, what's the wavelength of this light in silica? Now, in the last question, we derived the formula that said that n1 lambda 1 equals n2 lambda 2. So if you want the derivation of that, go back to the previous question. Now, in this case, n1 is going to be 1 because that's the vacuum. N2 is going to be the wavelength of the light in the vacuum, which is 649 nanometers. So that's going to be lambda 1. N2 is going to be the 1.484. And lambda 2 is going to be what I'm looking for. I'm looking for the wavelength. It says answer in nanometers, so I can actually just plug in 649 for my lambda 1. So in this case, I would have N1 is 1 times lambda 1, which is 649, and this is in nanometers. It's going to equal N2, which is 1.484, times lambda 2, which is just lambda 2, and I will solve for lambda 2. Now question 7 asks, calculate the frequency of the light. I have two choices here. I can calculate the frequency of light once it's in the silica, because now I will have the lambda in the silica and I will have the velocity in the silica. The other way is to recognize that the frequency stays the same, so it doesn't really matter. I can use the speed of light in a vacuum, and I can use the lambda that they gave me here, 649 nanometers. So that's what I'm going to do. The equation we use is the standard velocity equation for a wave, which tells me that the velocity equals the frequency times the wavelength. V equals f lambda. If I'm using the index of refraction here, if I do use the speed of light before it gets in, and I'm using the 649 nanometers, then the v is going to be the c, the speed of light, equals the frequency times the wavelength. So the frequency is just going to be the speed of light divided by the wavelength in a vacuum, so that's going to be 3 times 10 to the 8th meters per second divided by my wavelength, and here I will have to include the nanometers because I'm going to want frequency in hertz, so that for me would be 649, and again nanometers is times 10 to the 9th meters, 10 to the 9th, minus 9th, 10 to the negative 9th will give me my frequency, and it's going to be a very large number.